Alright, so hello everyone. This is the last unit for Avionics module. In this lecture, we are going to study about air data indicator. So some of the examples are your altimeter, airspeed indicator. So we are going to study about all these in detail. Now, along with these indicator, we are also going to study about different sensors that are used for measuring temperature and pressure. Okay, so some of the dial panels. So if you enter into the cockpit of an aircraft, you will see many dial panels. Okay, many measurement instruments. So some of the dial panels, they are your air data indicator. And from the previous classes, you may remember that these air data can be used to estimate the location of an aircraft. In case your GPS or satellite navigation system, it fails. So in that case, in case of emergency, we can use the air data to estimate the location of the aircraft. Okay, so obviously these air data indicators, they are quite important. And in general, keeping a track of air data is also important for maintaining or tracking the health of the aircraft. Okay, so how much pressure it has, withstand so far. Okay, so all that we can do using the air data information. Okay, so let us start with a little bit of introduction. So air plays a very important role in aviation. It helps in holding up the airplane and act as a medium for aviation travel. Now air is a gaseous mixture, we all know about it, and basically it consists of 78% nitrogen, 21% is oxygen, and you have 1% of other inert gases and greenhouse gases, something like argon, carbon dioxide, and ozone. Okay, now this atmosphere, you might have studied about this in maybe your geography classes or in your school days, right? So this atmosphere above the Earth surface, it extends from the surface of the Earth to all the way up to 105,000 feet. Okay, so it's around 105,000 feet. Right? Now the atmosphere is divided into three regions. So we have the troposphere, which extends from the Earth surface all the way up to 36,000 feet from the Earth's surface. Then you have stratosphere, which extends from the troposphere, it's here, troposphere, up to around 65,000 feet. Then you have chemosphere. So chemosphere is basically you combine the mesosphere and thermosphere, we call them together as chemosphere. Okay, so the chemosphere, it extends from stratosphere up to your 105,000 feet. Above the chemosphere you have exosphere, which is nearly the boundary of the space, right? So in a way you can say when you are in exosphere you are in space. Okay, so this figure also tells like the spaceships, they fly in the exosphere, the satellite, they are in the thermosphere, but mainly your aircrafts, they fly in troposphere. Okay, so we are only concerned with the first 36,000 feet in which the aircrafts they fly. Okay, now there are multiple factors that an aircraft should consider while traveling through air. So for example, you have atmospheric temperature, atmospheric pressure, and airspeed. So having some avionic systems to measure these important parameters or these temperature and pressure, it is very important for us, right? Or important for the pilot. Now, the unit which we use to measure these atmospheric pressure and temperature and airspeed, it is the standard international unit, or in short we call it SI units. Okay, but a more common or non-standard unit in aviation is nautical miles. Okay, so generally in SI unit we use metrics, but a more common and a non-standard unit, it is your nautical miles. Now let us start by discussing about the atmospheric temperature. So different layer of the atmosphere, they have different relationship with temperature. Okay, so I have mentioned it in 3 points in the slide. So the troposphere has a linear relationship with the altitude. Okay, so as the altitude increases, the temperature will decrease. Okay, so as your altitude increases, the temperature it decreases in troposphere. In stratosphere, the temperature is fairly constant. It is around 218 Kelvin or minus 55 degree centigrade. Okay, then in chemosphere, the temperature starts to decrease with altitude. Temperature starts to increase with altitude. In troposphere, the temperature decreases with increase in altitude. In chemosphere, the temperature will increase if the altitude increases, right? Because in chemosphere you are moving closer to the sun. Okay, closer to sun. Okay, so that's why the temperature, it starts to increase. Okay, now aircrafts mainly fly in troposphere, so the temperature will decrease as the altitude of the aircraft increases. So this is related by the equation here. Okay, now T is the temperature, T0 is the zero altitude temperature, or the temperature at sea level or zero altitude. Okay, now L is the lapse rate. Okay, it is the temperature lapse rate, and it is a constant. Its value is 6.5 multiplied by 10 to the power minus 3 Kelvin per meter or degree centigrade per meter. Okay, now this is a rate of change of temperature. So either you measure the rate in Kelvin or in degree centigrade, the rate of change will be the same. Okay, and that is why we can use either of the units. Either you can use Kelvin per meter or centigrade per meter. Okay, because this is the L is the rate of change of temperature. Okay, now the H is the altitude in meters. Okay, so let's use that equation and try to solve a numerical here. Okay, so let's read the question. So the question, it says, what is the temperature at an altitude of 25,000 feet? So the value of H is given, but H or the altitude should be in meters. Okay, but this is given in feet. Okay, so we have to convert 25,000 feet into meters. Okay, we'll look into it. We'll have a look at the solution, but let's read the question first. What is the temperature at an altitude of 25,000 feet when the temperature at sea level is 15 degree centigrade? So zero altitude temperature, or the temperature at sea level, is also given. T0 or T0 is also given. Okay, so let's have a look at the solution. Yeah, so 1 meter, it is your 3.28 feet. So we can convert this 25,000 into feet, into meters, 25,000 feet into meters, or what I have done in this question is I have converted the Laplace rate per meter into per foot. Okay, sorry, I'm again calling it as Laplace. It's the lapse rate. That is the problem of teaching multiple modules. So this is the lapse rate. Okay, so I've converted it from per meter to per foot. Okay, and what I have done is I have basically, so 1 meter is 3.28 feet. So I have converted the lapse rate into degree centigrade per feet, yeah, by dividing it with 3.28. So that value, it comes out to be 1.98 multiplied by 10 to the power minus 3. Okay. So I'm not converting this. Okay. I'm converting the lapse rate. So the temperature at 25,000 feet, we can calculate the value by using this equation. So we already know T0, it is 15 degree centigrade. The lapse rate, we have converted it, and it is 1.98 multiplied by 10 to the power minus 3 degrees centigrade per feet, and h, the altitude, it is already in feet. Okay, 25,000. So if we substitute the value and calculate it, we will get minus 34.5 degree centigrade. Okay. Now another way of solving this is to convert 25,000 feet into meters. Okay, and then use this value 6.5. So you can calculate it in that way also. It should give you the same result or the same value. Next, so the next physical parameter that we need to understand before discussing about the air data indicators is your atmospheric pressure. So the atmosphere is held to Earth surface by gravity. So similar to all the objects on the Earth surface, the atmosphere also experiences gravity, and gravity pulls it down to the Earth surface. Okay. So basically air is a compressible fluid, and its pressure depends on how much air is above the point where the pressure is measured. So basically your atmospheric pressure is the pressure of air above that point. Okay, and that is called as static pressure. Okay, so you might have heard about this blood pressure. So some some people have this health issue of blood pressure, either high blood pressure or low blood pressure. So what happens is, in a healthy human, the amount of your blood pressure, so when the blood is flowing in the body, it will exert an outward pressure, and from the atmosphere we are experiencing the atmospheric pressure. So for a healthy human being, it balances. So you don't feel any kind of, heavy or pressure. But if the blood pressure falls, then you will start feeling. So that means if you have low blood pressure, you can feel the atmosphere, the pressure of the atmosphere. Okay. And if your blood pressure is high, that means your body or your pressure because of the blood flow is more than the atmospheric pressure. Okay. So basically the thing we need to understand is the static pressure is the pressure at a point where which is because of the air above it. So static pressure is static, that is stationary, when the object is not moving. Okay. So static pressure is static, or another word for static is stationary. Okay. That is not moving. Okay. So if an object is not moving, it will experience a static pressure. But in the case of aircraft, because it is moving through the air or the atmosphere, it will experience another type of pressure which we call as dynamic pressure. Okay. So the next point on the slide, it says motion through a fluid may vary the pressure, and that can be calculated by this equation here. So PS is the pressure in millibar, MB, it is your millibar. Okay. And HP is the pressure altitude in meters. That is the pressure at any given altitude in meters. Now flight level, so sometimes you may get this word, you may get this flight level, okay, in a numerical or otherwise also. So flight level is the pressure altitude in feet divided by 100. So for example, this 27,000 feet pressure altitude, it will be flight level 270. That is, if you divide it by 100, that will be your flight level. So the actual altitude will be 27,000 feet. Okay. So if you are given with the flight level, you have to multiply it with 100 to calculate the actual altitude. Now let's take a question or a numerical based on this formula. So the question, it says, what is the pressure at 10,000 feet pressure altitude? Okay. So the first step is to convert 10,000 feet into meters. Okay. Now we already have this equation here. So the altitude is in troposphere, 10,000 feet is in troposphere. So we can use this equation, and we have already seen the conversion. So 1 meter is 3.28 feet. Okay. So if you calculate 10,000 feet, or if you convert it into meters, basically you have to divide 10,000 by 3.28. Okay, so I have just substituted the value here and converted it into meters. Okay, now you have to do the calculation a little carefully, but if you do it carefully, you should get this value, that is 696.5 millibar. Okay, so this will be the pressure at 10,000 feet, atmospheric pressure. Okay, so this will be your static pressure. At 10,000 feet. Now, having discussed about the general discussion about the temperature and the atmospheric pressure, now we can discuss about the first air data indicator, which is your altimeter. So an altimeter is an instrument that is used to measure the altitude of an aircraft. Okay. Nowadays there are more advanced altimeters. So you have something like radio altimeter, which uses radio wave to measure the altitude of the aircraft, and then also you have some GPS altimeter, so which uses GPS location and the signal to find out the altitude of the aircraft. Okay, so there are some more advanced altimeter available, but today in this class we are going to study the most basic type of altimeter, which is called as your barometric altimeter. Okay, so this barometric altimeter, it measures the pressure difference at different altitude to calculate the height of the aircraft. Okay, so basically it consists of an aneroid. Okay, this one here. Okay, so it consists of an aneroid which is then placed inside a sealed container. Okay, so this is your sealed container. Okay, now the aneroid, it is filled with air at sea level. Okay, so aneroid is filled with air at sea level, and a portion of the air from fuselage of the aircraft is allowed to flow into this sealed container, right? So this sealed container, it is connected to a static port. So static port, it allows some portion of air from the fuselage fuselage of aircraft. So static port, it will fill the container with the air from the fuselage. So it will provide a static pressure, okay, around this aneroid. So inside the container you will have static pressure, right? That is the air which is not moving, but it will be the static pressure at certain altitude in which the aircraft is flying. Okay. Now, if the aircraft, it is flying at an high altitude, then the pressure around the aneroid will be less. Okay. And the aneroid will expand. Okay. So at high altitude, the pressure will decreases. That means you will have low pressure around the aneroid, and the aneroid will expand. And at low altitude, the atmospheric pressure, it increases, so aneroid will contract. Okay. So if you try to relate it with the previous discussion of atmospheric pressure, so atmospheric pressure, it is the pressure because of the atmosphere above a certain point. So if you are at high altitude, there is less atmosphere above you, so the atmospheric pressure will be less. If you are at low altitude, there will be more layer of air or layer of atmosphere above you, so you will experience more atmospheric pressure. Okay, so atmospheric pressure at low altitude will be high or it will increase. Okay, and based on that, this aneroid will either expand or contract, and this aneroid is then connected to a gear and lever assembly which can drive a needle, okay, to display the altitude in feet, right? So it will drive a needle on the dial panel, and it will tell you the altitude of the aircraft in feet. Okay. Now here is an animation to demonstrate how your barometric altimeter works. So altitude increases, pressure decreases, aneroid expands and drive the gear, and when the altitude decreases, the atmospheric pressure increases and the aneroid contracts, and again it will change the readings on the altimeter. Okay, static port, it is always providing the static pressure from the fuselage. Right. The next air data indicator that we are going to study is your air speed indicator. Okay, so the airspeed, it is the velocity of an aircraft through air. Okay, now if the air is moving relative to the ground, the speed, this speed, it is the vector sum of the aircraft velocity in air and the vector velocity of air relative to the ground. Okay. In general, to understand it, basically if you have your aircraft and if you have a tailwind, that means the aircraft and the air, they are flowing in the same direction, then your effective speed will increase. In vector addition, we also consider the direction. Okay. So if they are in the same direction, the effective speed will increase. But if they are in opposite direction, the speed will decrease. Yeah. So that's why we do vector addition of aircraft velocity and the air velocity. Okay. Now in aviation, the airspeed is measured in knots. And we have a much older unit, which is miles per hour. Okay. Now, although there are aircrafts which can fly above the speed of sound, generally your fighter aircrafts or military aircrafts, they can fly above the speed of sound, but in general we operate the aircraft below the speed of sound. Okay. Or maximum at the boundary of the speed of sound. Okay. We don't try to exceed the speed of sound in normal operation or in normal flight. Okay. Because what will happen is the faster you fly will cause more structural damage. So if the aircraft is flying at very high speed or the speed of sound or more than that, then your structural damage will increase. Okay. So to avoid it, we try to operate in general below the max speed or the speed of sound. Okay. Now the speed of sound, it is given by this equation here. Vs is the speed of sound in meters per second, and T is the temperature in Kelvin. Okay. Let's again use the equation and try to solve a numerical. It's basically a very short numerical. So let's read the question. So the question says, what is the speed of sound in stratosphere? Okay. So to use this equation, to find the speed of sound, we need to first of all know the temperature in stratosphere. So temperature in stratosphere, in the first slide which we have discussed, in stratosphere it is constant. The temperature is constant. It is minus 55 degrees centigrade or 218 Kelvin. Okay, so we can use the value. So I've used 218 Kelvin and simply calculated it. So you will end up getting 295 meters per second. So this is the speed of sound in stratosphere. Okay. Now, Mach number. So a measure of airspeed in high performance aircraft is called as Mach number. Okay, so it is an airspeed relative to the local speed of sound. Okay, so your Mach number, it is denoted by capital letter M, and it is given by this equation. So Vt is the true airspeed and Vs is the speed of sound. And in general, the speed of sound, it is we have calculated it, it's around 295 meters per second. Okay. Now we have another numerical kind of combining three of the formulas, okay, or three of the equations. So let's read the question. So an aircraft is flying at an assigned altitude of 15,000 feet. Okay. Now the temperature at sea level is 24 degree centigrade and the true speed Vt, it is 525 knots. So we have to calculate the Mach number M, right, for the aircraft. Now if you were just given with the true speed and you were asked to calculate the Mach number, you could have assumed the speed of sound to be 295 meters per second. But here in this question, you are given with the altitude and the temperature at sea level, T0. So using all these values, first of all, we will have to calculate the temperature at 15,000 feet and then use that temperature to then calculate the speed of sound, Vs. Okay, and then use Vs. So we cannot use this value 295. We have to calculate it. Okay. Now, first of all, we'll need some unit conversions. So what I've done here is I have converted the true speed, that is 525 knots, into meters per second. So 1 knots is 0.0 0.514 meters per second, and 1 feet is 0.305 meters. And so I've converted the altitude, the 15,000 feet, into meters. Then we are given the temperature. It's in degree centigrade, and we have to convert it in Kelvin. So 0 degree centigrade, it is your 273.15 Kelvin. Okay, so 24 degree centigrade will be 24 plus, don't multiply it, right, add it, 24 plus 273.15. So approximately, if you ignore 0.15, you will get 297 Kelvin. Okay, so I have converted all the values, and then I will first calculate the temperature. Okay, so T0, I have converted it in degree centigrade. L, it is a constant, so 6.5 multiplied by 10 to the power minus 3. So this is E minus 3, it is 10 to the power minus 3. Okay, and then you have the altitude. So 15,000 feet, we have converted it in meters. So using all those values, if you calculate the temperature at 15,000 feet or 4,573 meters, it will come out to be 267 Kelvin. Now using this temperature, we will then calculate the speed of sound, Vs. It's quite simple and straightforward. So the speed of sound at 15,000 feet, it comes out to be 327 meters per second. Okay, and then we can use this value to calculate the Mach number. So true speed, so from knots we have already converted it into meters per second, and that comes out to be 270 meters per second. And Vs, we have just now calculated it, so we can use that value. So the Mach number, it comes out to be 0.83 Mach. Okay, so it's flying below the speed of sound. So if you have Mach 1, that is your speed of sound, and if you have higher value 1.2 or 2 Mach, like that, so that means you are going above the speed of sound. Now the next indicator is your air speed indicator. So before discussing about the working of your airspeed indicator, let's try to understand about this pitted tube. Okay, so basically static pressure is the pressure of air that is stationary or is not moving. Therefore, static pressure does not increases. Okay, static pressure at any point or at any altitude will be the same. It will not increase or it will not change. Okay, whereas your dynamic pressure, it is the pressure that changes due to airflow. Okay, so I have not mentioned it here. Dynamic pressure is it will change, and it is mainly because of the airflow. And it changes depending on your speed. Okay, now the total pressure, sometimes it is also called as ram pressure. Okay, so it is the sum of both static and dynamic pressure. So this total pressure or ram pressure, it is obtained from your pitted tube. So this is your pitted tube. Okay, the dotted one. So pitted tube, it has a small opening here. And generally the pitted tube, it is placed in front of the aircraft. So what will happen is, through this small opening, the air will be forced into the tube. Okay, so you have the aircraft and you have generally your pitted tube fixed here. So the air will be forced into your pitted tube. Now, to calculate the airspeed, we need dynamic pressure. Okay, so for calculating the airspeed, the main thing that we need is the dynamic pressure. Which basically changes due to the movement of the aircraft. So therefore, the difference between the total pressure and the static pressure, it can be used to calculate this dynamic pressure and the airspeed. Okay. Now the ratio of the total pressure to the static pressure, it is given by this equation at the bottom of the slide. And this equation basically, it relates your Mach number with the two pressure, the total pressure and the static pressure. Okay. Now, I have already discussed all these points. Basically, your indicators used to measure the atmospheric pressure, the altitude. So this is your altimeter, and you have the airspeed, indicator, and this is your atmospheric pressure, right? So this is the general arrangement of all the indicators, right? Or this is the way your indicators, they are connected. And obviously you have your pitted tube. Okay. Now let's go into the working of airspeed indicator. So the airspeed indicator, it has a similar setup as the barometric altimeter, which we have just now discussed. However, in the airspeed indicator, the pitted tube is connected to this diaphragm, right? So now we are calling this thing as diaphragm. Okay, diaphragm or aneroid. Okay, they are the same thing basically. So since you are connecting the pitted tube to the diaphragm, you will have total pressure inside the diaphragm. Okay, so this diaphragm will have total pressure. So total pressure is static plus dynamic pressure. And then you will have a static port which will be connected to this sealed container. So there you go. I think this is the static port. And it is connected to your sealed container. So static port, it will provide air from the fuselage, right? So around this aneroid, you will have static pressure. Inside the aneroid, you have static plus dynamic pressure. Okay. Now, if the aircraft is moving at high speed, the pressure inside the diaphragm will be more than the outside. So the diaphragm will expand. Okay. And if the aircraft is flying at low speed, the pressure inside the diaphragm will be less than the outside, so it will contract. Okay. So diaphragm, again, it is connected to some lever and gear assembly, which will then drive your needle. Okay, it will drive the needle on the dial panel, and it will show the airspeed in knots. Okay. Again, I have an animation here. So this is the animation for airspeed indicator. So inside the diaphragm, you have total pressure, that is dynamic plus static pressure, and outside you have only the static pressure. Okay, from the static port or from the fuselage. So therefore, if the dynamic pressure increases at high speed, the diaphragm will expand, and if the dynamic pressure is low, at low speed, the diaphragm will contract. Okay, so basically dynamic pressure, it depends on the speed of the aircraft. So if it increases, the diaphragm will expand, and if it decreases, the diaphragm will contract, and accordingly it will move the needle on the dial panel to show you the speed in knots. Now, the next air data is your temperature. So to measure the air temperature, what we do is the bulb of the thermometer. So we use a thermometer, and obviously in a thermometer you have the end or the bulb. Okay, and then you have your thermometer. You can use a digital one or the mercury thermometer, whichever, but you have a end which is sensitive to temperature. So that's your bulb. So the bulb of the thermometer, it is pushed through a hole in the fuselage of the aircraft, like that, and then you have your aircraft body, right? So it is pushed outside, but this temperature will be the air temperature plus the temperature due to kinetic energy of the airstream. So if you just push a thermometer outside the aircraft, you will have the air temperature plus the temperature due to the friction or the kinetic energy of the air. So this is called as total outside air temperature, or in short TOAT. Okay, so obviously we don't need the total outside temperature. We only want to measure the air temperature. Okay, so in this case, in the first case, your air will produce some friction, and because of that your temperature will be higher. Okay, so what we do is we cover this thermometer. Okay, so to avoid additional temperature due to kinetic energy, the thermometer is covered or shielded, right? So now in this case you will only measure the outside air temperature, okay, or OAT. Okay, so generally we use a thermometer and it is shielded to avoid the additional temperature due to kinetic energy. Now the temperature tends to rise at high velocity. So if you are flying at very high velocity, the temperature, it will increase, and above Mach 1, that is the above speed of sound, due to the air friction, the temperature will rise more. Okay, now to give you an example of how much this temperature due to air friction can be, is your space shuttle. So you might have heard about the space shuttle Columbia disaster, right? So where while going into the space, uh, one of the tiles, so generally these space shuttles, they have some heat protective tiles. So the entire space shuttle is covered with some heat protective tiles. So while going into the space, one of the tile, it fell off, or because of some malfunction, it was spoiled or detached from the space shuttle. So while re-entering or while coming back to the Earth, because of the air friction, the temperature inside the space shuttle, it increased dramatically, right? And obviously the disaster happened, right? So you can imagine how much of a temperature increase or a temperature change the air friction can cause. Okay. Now for aircraft, temperature measurement is important because it warns about the ice formation, that is warning of ice, right, which may be due to the moisture deposition, and when the aircraft is flying at high altitude, that moisture or that water droplets, they freeze and they cause some problem if they freeze within some critical parts of the aircraft. So that is why air temperature indicators or measurements are quite important for aircrafts. Okay. Now, modern aircraft, they use a computer which is called as air data computer. So this air data computer, or ADC in short, it converts pressure and temperature into electrical signal. Okay. Then the processed signal is then sent to the different indicators and automatic flight controller. Okay. So this computer will collect all the air data from the sensors and then process it and send it to the indicators and automatic flight control system, okay, in the modern aircrafts. Now the ADC takes these data from different points on the aircraft, process them and distribute them to the indicators. Almost the same thing. Now, the mechanical indicators that we have previously studied, they use lever and cams and some non-linear spring, right? So they use lots of mechanical things in them. So these mechanical instruments, they are first of all quite heavy, and then they are quite expensive, and also they would need regular calibration from a trained technician, right? So altogether they are not very useful, or nowadays they are present in the aircraft just in case your digital indicators they fail, but then again they increase the weight and they are relatively expensive. Okay, so therefore the alternative for these mechanical indicators, nowadays we use sensors, okay, to digitalize the output. And you have your ADC, which will compute the parameters with higher accuracy, reliability and low cost. So these sensors are relatively cheaper, very cost effective, and to a certain extent they are reliable, and yes, they have very high accuracy in comparison to your mechanical indicators. Okay. So the last thing that we are going to discuss is about these sensors. Okay, so sensors for pressure and temperature measurements. So first of all, let's start with the pressure sensor. So we have seen that pressure measurement, it is the basic for calculating the airspeed, the altitude, and along with that the pressure can be used, or the pressure value can be used to calculate the Mach number and the rate of climb and so many other measurement. So the first type of pressure sensor, it is your capacitive pressure sensor, right? So in the figure you could see it consists of two metal plates. Two metal plates. Now one of the metal plate is on a fixed surface. Okay, the bottom one, it is on a fixed surface, whereas the second metal plate, it is on a flexible. Right? That means you have some kind of a diaphragm and you paste a metal plate on that diaphragm. Okay. So whenever some pressure is exerted on the diaphragm, okay, the diaphragm will deflect, and as a result the distance between the two plates, it will change. Now we all know that the capacitance is proportional to the distance between the plates. Okay. So if the distance changes, distance between the two plates, it changes, then your capacitance value will also change. Okay. Now this change in capacitance, it can be calculated by this equation here. So it is given by the maximum change in capacitance, maximum change in the distance between the plates to the minimum change in between the two plates. Maximum distance to the minimum distance, okay, between the two plates. So let's use this formula to calculate some value or use it to solve a numerical. So the question here, it says that how much will the capacitance change for a pressure transducer if at 3000 feet pressure altitude the separation of the plates is 0.5 millimeter. Okay, so the aircraft is already at 3000 feet and the distance or the separation between the two plates is 0.5 millimeter, and the total deflection from 3000 to 50,000 feet is 1 millimeter. Okay, so the aircraft is at 3000 feet and then it is going all the way up to 50,000 feet. Okay, and in that case the change in the distance between the two plates, metal plates, is 1 millimeter. So we are going to use this formula, right? So the maximum deflection, it will be 0.5 plus 1. Okay, so this is not the aircraft is not at ground or at sea level. It is already at 3000 and then it is going up to 50,000. So the maximum deflection will be 0.5 plus 1. That is altogether 1.5 millimeters. And the minimum deflection, so the aircraft was at 3000 feet, so the minimum deflection was 0.5 millimeter. So the change in capacitance, it will be 1.5 divided by 0.5, that is 3. Okay, so this will be unitless. You won't have any unit. Okay. The next type of pressure sensor is your strain gauge. Okay, so you might have seen this formula for resistance. So your resistance R, it is rho L divided by A. Okay, L is the length, A is the area of cross section of any wire or metal. Okay, and rho is the resistivity of the material, right? So if you use gold, you will have less resistivity. If you use maybe iron, aluminium, it will have relatively higher value of resistivity. So it depends on the material of the wire. Okay, so if we stretch the wire or the resistor, what would happen is you would change the length. Okay, so if the initial length was L and you are stretching the wire, it will change its length, and also the cross section area will decrease, right? If you're stretching something, it will become thin and it will become longer. Okay. So in a way, if you stretch the resistor, the value of resistance will change because of the change in physical dimensions. Okay. So in strain gauge sensor, it includes a set of thin film resistors that increases resistance when they are stretched. Okay, so these are special type of resistor. They have a thin film on it, and if you stretch it, the value of resistance will change. The four resistors, they are placed on a diaphragm, something like this. You have like four resistors here, and they are placed on a diaphragm similar to your capacitor sensor. And when the diaphragm experiences pressure, it deforms and stretches the resistor, which changes the resistance and the output voltage. So this output voltage is then measured to calculate the change in pressure. Okay. Now, moving on to the temperature sensor. So there are three types of temperature sensor used in an aircraft. The first one is your thermocouple, which is one of the most common and reliable temperature sensor. And if you have used multimeter, or you might have seen this type of a sensor, this wire. So this end portion of this wire, it is your thermocouple. Okay, and this sensor basically it includes two copper wire, and the end of the copper wire, they are soldered together, they are joined together. And when this end it is heated, then what will happen is the heat will flow through one of the wire, and the other wire will be at room temperature, or it will be cold. So because of this hot and cold junction, some very small amount of voltage or electricity is produced, or it will flow between the two wires. Okay, and we can measure this using a voltmeter. So based on the amount of voltage produced, you can then calibrate it to measure the temperature. Okay, so because of hot and cold junction, you will have a small voltage between the wires. Okay, and you can measure it to calculate the temperature. The next type of temperature sensor, it is your semiconductor sensor. Okay, now semiconductor, they are of two types. So you have a p-type semiconductor and a n-type semiconductor. So p-type semiconductors, they have more number of holes, okay, or positive charges. And n-type semiconductor, they have more number of electrons or negative charges. Okay, so in semiconductor sensor, what we do is we take a p-type and a n-type semiconductor and join them together. Okay, something like here. So we join them together. So as a result, what will happen is the positive charges from the p-type and the negative charges or the electrons from the n-type, they will move at the junction. Okay, they will move into each other because opposite charges, they attract each other, right? So the holes and the electron will start moving towards the junction. So at the junction, what will happen is you will have accumulation of positive and negative charges at the junction, and a situation will arise when the number of positive and the number of negative charges, they become equal. Okay, and as a result of that, at the junction you will have a depletion region will form. So this depletion region will be the region where you have no charges, or it will be neutral. Right? So you have equal number of positive and negative charges at the junction. That means positive and negative, they will cancel each other, and at the junction you will have a neutral region. So this neutral region, which we call as depletion region, it will act like a barrier. Okay, and obstruct any further flow of charges, either electrons or holes. Okay, so when you join P and N, you will have a barrier region in the middle. Okay, because of this depletion region. Now what we do is we apply a bias voltage. Bias voltage is a voltage basically. So we apply certain amount of voltage. Now this voltage is, its value is such that, so when you apply this voltage, what will happen? You have connected the negative terminal to this side. So negative terminal means electrons will flow into the N region, okay, from the voltage source. You are supplying additional amount of electrons in the N region, right? So imagine you have a wall in front of you. Initially only 10 number of electrons, they were pushing that wall, right? It was not breaking. But now with the help of voltage, you are increasing the number of electrons to maybe 10,000. Just an example. So if 10,000 electrons are pushing the wall, it will break. Yeah, so that's the whole concept here. So what we try to do is we apply a voltage just sufficient to maintain this barrier. Okay, so you have just sufficient number of electrons that the barrier is still there, but even a little bit of extra energy if you apply, the barrier will break. Okay, so we select and tune the voltage to that value. Okay, and when the temperature, when we use this biased semiconductor sensor as a temperature sensor, what we do is we increase the temperature around this. So as the temperature increases, this barrier will break because you have already applied a small voltage which is just holding the barrier, and any additional heat energy will break the barrier. Okay, so if the barrier breaks, the electron will be able to flow into the P region, and as a result your circuit will be complete and some amount of current will start flowing in the circuit. So that current we measure to calculate the temperature. Okay. The last type of temperature sensor is your RTD or resistive thermal device. They are also called as thermistor. Okay, so we all know that resistance is the opposition in the flow of electrons in any circuit or any material. Okay, however, the resistance of the same material will be different at different temperature. Okay, generally at high temperature the resistance will be low because the electron they get that extra heat energy allowing or pushing them to flow. So generally if you heat the material, the resistance decreases. So this fact is used to measure the temperature. Okay, so in thermistor we use some metal oxide. Okay, so they are made out of some metal oxide, something like your nickel oxide or copper oxide. Okay, and when these material or this thermistor is heated, or the temperature around the thermistor it changes, the resistance will also change, and therefore we use an ammeter to measure the value of current. Okay, and based on the value of current we can then calibrate this sensor to measure the temperature. Okay, so thermistor or RTD basically they work on the principle that same material at different temperature have different value of resistance. Okay, so this is the working principle of your thermistor. Right, so this is the end of today's lecture.